So I want to give you a quick rundown of waveform and show you a couple of textbook waves as a way of reinforcing that, and also connecting those ideas of waveform to timbre and harmonic content. Now, you may have heard of these terms before in audio production, but what do they mean? Well, waveform is the shape of the wave, literally the form of a particular wave. And in Pro Tools, we typically see that as a graph showing the amplitude of a signal at any moment in time. Now, the timbre is the perceived sound of the wave, how it sounds to us, the tone color. We might use terms like rich or hollow or brassy or thin to describe timbre. And the harmonic content is the actual specific blend of harmonics that give a particular wave its sound. Now, the interesting thing about these three terms is that they're connected. They're related to each other. If you change the waveform, the timbre of the wave will change, and its harmonic content will change. Likewise, if you change the harmonic content, you filter or you EQ a sound, you are changing the waveform, and you are also changing the waveform's timbre. So what I have here is a sawtooth wave. Now, before we get into the specifics about the sawtooth wave, let's take a look at this graph. We have a grid here, and the vertical lines in this grid represent frequencies that are an octave apart. For example, from 40 Hz to 80 Hz is an octave, from 80 Hz to 160 Hz is an octave, from 160 to 320 is an octave, etc. The horizontal lines of the grid are separated by 6 decibels of level. So higher on the grid means you have a stronger wave, and lower on the grid means a lower level. Now, for this sawtooth wave, you can see that I've got a frequency of approximately 80 Hz. That is the fundamental on the left, and it is the loudest and lowest of the harmonics. You can see the shape of the waveform in the upper right against the yellow background. This is a perfect sawtooth wave from Reason's subtractor. This graph has been generated by something called a fast Fourier transform. In a perfect world, we would have a vertical line segment at a very specific frequency, but what the fast Fourier transform does is it trades a little bit of the accuracy of the display for speed, and this is something that can run in real time. So a couple things we notice, that instead of a perfect line segment at 80 Hz, we see a sort of peak, a spike, if you will, that's getting wider as it goes down. And we see one also at 160. We see one at approximately 240 Hz. And then we have one at roughly 320, and so on and so forth. Now, one of the things that you're going to notice is that these are evenly spaced in Hertz, but because our frequency scale on this graph is logarithmic, it's actually a pitch graph, which shows equal octaves as equal space on the graph. The harmonics are getting closer together. So there is one harmonic between 80 and 160. There are 2 between 160 and 320. There are 4 between 320 and 640. There's 8 between 640 and 1.3 kilohertz, and so on and so forth. Each octave doubles the amount of harmonics. So above 1.3 kilohertz on this graph, we don't see the individual harmonics anymore. They're kind of smearing together. And that's just simply a function of the fast Fourier transform. It's not super accurate, but it is giving us the rough idea. One thing you do notice here is that there's a steady rate of level drop as we go higher in frequency. So that's the sawtooth wave. Now let's take a look at the square wave. And in the square wave, we see something very similar. First of all, we have in the inset against the yellow background the actual waveform. And we see the fast Fourier transform has a similar slope as we saw with the sawtooth wave. But in this case, we only have odd-numbered harmonics. So their spacing is a little more far apart. And in fact, we can see up to about 3K, the individual harmonics. And then they start smearing together as we go above that. The next wave is a triangle wave, and it's also a blend of odd-numbered harmonics, but it tends to favor the low-numbered odd harmonics. So we have harmonics here. I can see the 1st, the 3rd, the 5th, the 7th, the 9th, the 11th, the 13th, 15th, 17th, 19th, 21st, 23rd, 25th, 27th, and the 29th harmonics on this graph. Finally, a sine wave. Again, you see the waveform against the yellow background, and you see that this is just picking up a single frequency at just above 80 hertz. Now, if we were to annotate this, we can see a couple things here. We have the first harmonic labeled 1, the second harmonic is labeled 2, the third and the fourth, and so on. And you can see that those are getting lower in level as we go higher in frequency. And since every octave represents a doubling in frequency, the octaves of the fundamental are showing up on vertical grid lines. So we have the second harmonic at 160, we have the fourth harmonic at 320, the eighth harmonic at 640, the 16th at 1.3 kilohertz, the 32nd at 2.6 kilohertz, the 64th at 5.1, and the 128th at 10 kilohertz approximately. Another thing about this is I have included some formulas at the bottom. They're actually very simple and easy to understand. The frequency of any harmonic, let's say the nth harmonic, is simply the frequency of the fundamental, the first harmonic, marked on the graph as 1, times n. So if our first harmonic is at 80 hertz, and our seventh harmonic would be 7 times 80, or 560 hertz. The second formula is the amplitude of any harmonic. So the nth harmonic, its amplitude will be the amplitude of the fundamental, A1, times 1 over the number of the harmonics. So again, the seventh harmonic would be 1/7 the amplitude of the first harmonic. Our decibel scale is logarithmic as well, so you can't apply those numbers directly to the amount of decibels. But if you do a decibel conversion of 1/7, you're going to find that it's about 16 or 17 dB below the fundamental. Essentially, the rate of level drop as we go higher in harmonics is roughly 6 dB per octave. So every octave is 6 dB lower than the previous octave. In this graph, the square wave, we've done the same thing, but you'll notice that the second, fourth, and the sixth harmonics are absent from the square wave. And in fact, all of the even-numbered harmonics are missing. But we still have the harmonic number is going to be a multiple of the fundamentals. So to get the frequency of the third harmonic, you multiply the first harmonic's frequency by 3. And the amplitude, again, is the first harmonics times 1 over the harmonic number. So the third harmonic is 1/3 of the strength of the first harmonic. And that's roughly about 9 dB drop in level. Okay. So we have the same kind of slope, 6 dB per octave, as we had with the sawtooth wave. And if we go back and forth between the waves, sawtooth, square, sawtooth, square, sawtooth, square, you see the slope is the same. When we look at the triangle wave, though, the slope is steeper. So the rate of level drop for the higher harmonics is more steep, and it's essentially 12 dB per octave. Now, the way you would calculate it would be to take the harmonic number, let's say the third harmonic, and that would be 1 over 3 squared, or 1 over 9, times the first harmonic. So this is going to produce a significant drop in level, and essentially, as I said, this will follow about a 12 dB per octave drop as we go higher in harmonic number. And of course, looking at the sine wave again, we see there's only the one harmonic. It's a pure tone.